Okay, in that case, welcome everyone to today's session of the APCTP workshop, Holography 2022. And our first speaker today is Tom Hartman from Cornell University. And he will tell us about coarse graining pure states in AdS and CFT. So please, Tom, the floor is yours.
Okay, thank you very much for having me at this nice workshop. So I want to tell you about work from June with my student Jivan Chandra. So I'm going to start with a few words of motivation and introduction. Two-dimensional gravity is holographically dual to a random matrix theory. This was discovered a few years ago. And this seems to be a fundamentally different duality from earlier string theory examples of AdS CFT, at least on the surface, because the boundary theory here is not quantum mechanics. Random matrix theory is not quantum mechanics. For example, observables in two copies of the boundary theory don't factorize. If you are doing quantum mechanics, then the partition function is just a number. So the partition function, two copies of the partition function are just the product of two numbers. But in random matrix theory, that's not the case. These are correlated by the disorder. And similarly, in the bulk, there are topologies that connect two boundaries and contribute non-factorizing terms to something like the product of two partition functions or other more complicated observables. And this is best understood in two dimensions, but there are many reasons to suspect that averaging or coarse graining or some kind of ensemble plays a role also in higher dimensional gravity. This isn't just restricted to two dimensions. For example, there are spacetime wormhole saddles with no known instabilities in higher dimensions, which seem to contribute some non-factorizing terms to multi-CFT observables. So this is clearly something. Is there a question?
Yes, I have a question. So,
please.
I mean, when people say holography, we can imagine that the background is fixed, and then we compare with the CFT naively. So here, when you say 2D gravity is holographic due to the random matrix, here it seems that you also consider this topological summation of the whole or geometry. So is it something like some general concept of the holography, or?
Well,
or is it really consider quantum gravity is due to the CFT?
Yeah, so in quantum gravity, we're integrating over metrics, so it's reasonable to include different topologies. There are some situations where we know that you must include different topologies. For example, the Hawking-Page transition is a case where, in order to match the phase structure of the dual CFT, you have to include different topologies in the bulk. Now, we don't have a complete general understanding of which topologies you're supposed to include. And until recently, many people would have said that these connected topologies are simply excluded from the gravitational path integral, that we just shouldn't include them. But that seems to be too quick. It doesn't seem to be the right answer, at least not the best answer, because what we've learned from things like this JT random matrix duality is that there's interesting and universal and important physics being encoded by these wormholes, and so we should figure out what it's telling us about the microscopic theory. Okay, so this is really this general problem of understanding the role of these higher topologies in higher dimensions is a very important one.
Excuse me.
Yes, is there another question?
I have some related question. So, from 2D gravity point of view, including wormhole-like an object is very natural, but from matrix point of view, why this just the product partition function should contain this instanton or wormhole-like an object?
So the matrix integral is viewed as an averaging over theories, and so when you do this calculation in random matrix theory, you take the partition function of the theory, you square it, and then you average over the theory, say over the Hamiltonian of the theory. That's the random matrix in this random matrix theory. In random matrix theory, the way this calculation is done is that you square something and then you integrate over the matrix. So in that case, it's acceptable and expected to have correlations between the two copies. They're correlated by this disorder integral.
Here also the disorder is playing the role.
Sorry, I couldn't hear that.
Here also, I mean maybe just you are you are looking at the matrix as just 2D gravity, maybe simply, I guess. But it's a bit mysterious why the factorized two partition function should contain this instanton of configuration.
Yes. From the point of view of quantum mechanics, this cannot happen, and that's why it's interesting. It's the fact that these are things that seem to be excluded by quantum mechanics. So it seems that there must be some kind of. It seems that the bulk gravitational theory is not calculating what we thought it was calculating. It's not calculating factorizing quantum mechanical amplitude. It's calculating something which, in this case, has a ensemble average over quantum mechanical theories. And more generally, we don't know exactly how to think about that average in higher dimensions. But that's what I'm going to do in this talk is to give another way of interpreting these sorts of connected contributions in a way that can be applied in higher dimensions and doesn't conflict with quantum mechanics in any way.
I see. Okay, thank you.
So a related comment here is that the point is we're not saying that a UV complete theory of quantum gravity requires disorder or an ensemble average, just that the effective theory of gravity, that is Einstein gravity coupled to matter, seems to be, in some cases, calculating for us some coarse-grained or average quantities. And the task for us is to understand what sort of coarse graining or what sort of averaging is being done by that low energy effective theory and what observables are being captured. So this raises the question, what is the role of higher topologies and multi-boundary geometries in more than two dimensions, bulk dimensions in quantum gravity? And in this talk, we'll study a particular class of spherically symmetric multi-boundary wormholes and their dual CFT interpretation. Before I get into the details, I just want to preview what these solutions look like. So these are solutions. So everything, essentially everything in the talk will be in any number of dimensions, d dimensions, and it will, for the most part, be spherically symmetric. And we're going to be talking about on-shell, so solutions of the gravitational equations of motion coupled to matter. And this is what they look like. So I'll draw a bunch of pictures like this. Let me explain clearly what this picture means. So this is a 6-boundary wormhole. Each of these black lines is a boundary with a round metric. So it corresponds, in this case, to 6 copies of the CFT, each living on a sphere. They're Euclidean solutions of the gravitational equations of motion with matter sources. The matter sources in this picture are the red lines. So this red line is a spherically symmetric matter shell or matter distribution that's extending from one boundary to the next. So each point on this diagram is a d-1 sphere. The whole thing is spherically symmetric. I will focus on the cases where there's a zk cyclic symmetry rotating the k boundaries, although these can be constructed, well, they certainly exist for non-zk symmetric. It becomes a bit hard to solve the equations of motion, however, if you don't have that symmetry. Finally, these solutions are generic in the sense that I'll discuss some examples, but solutions like this exist in any theory of gravity coupled to matter. And I'll explain why as we go. The details of the matter distribution, what we'll find is that for a particular matter distribution, there's an upper bound on K, the number of boundaries. Okay, so different types of matter allow you to have a different number of boundaries. Some types of matter will allow you to have a large number of boundaries in this picture and still have an on-shell solution. Other types of matter will restrict K to be something small. Sometimes the bound on K is even less than 2, in which case you can't have any extra boundaries. But we'll see that you can make sense of these wormholes even for non-integer K, which sounds strange because it's a non-integer number of boundaries, but it's something that makes sense both in the bulk and in the dual CFT. There's been discussion of other wormholes in d-dimensional AdS. This is not, so this is different from the wormholes that have been discussed previously. In particular, if you look at the sources that are required to turn on to create these wormholes, the sources don't involve any deformation of the theory at the boundary. There were some previous solutions in d dimensions which required some deformations of the theory. These don't, so this is going to be related to just the ordinary CFT that we usually talk about in AdS CFT. They are similar to wormholes that have been considered earlier in 2 dimensions, in particular in what's called the West Coast model of 2D gravity, which has JT gravity with matter and has a similar class of wormholes. And we've also considered a similar type of wormholes in 3 dimensions that I'll mention at the end of the talk. Okay, so those are the kinds of solutions that I'm going to be discussing. Maybe I'll pause here and see if there are any questions before I go on. Okay, so I'm going to start by giving some more detail on how these solutions are constructed. It's actually pretty easy to solve the Einstein equations in this.
Can I ask you a question?
Case. Yes, go ahead.
So in the previous figure, right, and the spherically symmetric matter. So these are living in the bulk AdS, but these are connecting to boundaries. So should we interpret this bulk matter as some kind of a dual of some CFT operator, or which is not related to boundaries over there?
Yeah, that's right. So since the matter hits the boundary here, that corresponds to an operator insertion. And I'll discuss this a bit later, but there's a sphere, since we have a spherically symmetric matter distribution hitting the boundary, this corresponds to a spherically symmetric operator inserted in the CFT. So this is roughly related to a 2-point function of that operator to k copies of that 2-point function. I'll get into this in more detail in a few minutes.
Right. So just because it seems a little bit different from the SYK case where disorder has nothing to do with those boundary fermions. But here, if we are thinking this meta field as some dual object in the boundary. Then this dual object, this meta field is playing the role kind of connecting object, just like in disorder. It's a little bit.
I wouldn't think of the red lines as similar to disorder connecting the theory. I would think of that as a probe of the disordered theory. Now it's true that in order to get on-shell solutions, you need the matter. You need to insert this matter, but it's not. It is similar to in SYK or in JT when people add a heavy particle as a probe. It's similar to that, and it's playing the role of that heavy particle or end of the world brain.
I see. All right, let's go. Thank you.
Okay, so I'm going to start by describing in detail how we construct these solutions, how we solve the equations of motion. It turns out to be quite easy. There are various ways of interpreting the wormholes. I'll focus on one of them, which is interpreting them as related to a coarse graining procedure. And I'll describe how we can use the wormholes to define what it means to coarse grain a pure state in a CFT. And then I'll conclude with a few remarks. First, a note on terminology here. I want to distinguish between ensemble averaging and coarse graining. And I'm using those terms a little bit differently. So I want to be clear what that means. By ensemble averaging, I mean that you average over theories. That is, you take some observable and then you average over Hamiltonians or Lagrangians or perhaps some data like OPE coefficients or other observables. But that's really an average over theories. Once you do an ensemble average, you should not expect to obey the usual rules of quantum mechanics. The other thing I'll be discussing is coarse graining. When I say coarse graining, I mean that we fix the theory and we calculate some coarse-grained observable in a fixed theory. So this is an ordinary observable in ordinary quantum mechanical theory, but it's one that's been designed to throw away some UV information, to be less sensitive to the UV details. So it's for example, in RG, you think of that as coarse graining. So that's just to clarify the distinction here, and I'm going to be careful about making that distinction because one of the points I want to make is that we can often interpret wormholes either using ensemble averaging or in terms of coarse graining. Okay, I'll begin with discussing these wormhole solutions. First, the bulk theory. These solutions exist for various types of matter. I'll focus on two examples. The first example is Einstein gravity coupled to pressureless perfect fluid. That is, to massive probe particles or dust. The second example is gravity plus end-of-the-world brains. These end-of-the-world brains, for our purposes, are just a particular kind of matter. The action of the end-of-the-world brain is simply what's written here. You take the ordinary Einstein action, you terminate the space-time at a brain, and on that brain, we have a Gibbons-Hawking-York term, the extrinsic curvature K, and we also add a tension term. That is like a cosmological constant on the brain. The tension has to be positive, but otherwise it's a free parameter. Okay, this is really, these two examples are really just to have some concrete examples to show you. I think that you can construct similar kinds of solutions with any reasonable matter in your theory. So before we get to the wormholes, I'll start by constructing black holes, explaining how we get black holes in the theory with pressureless fluid. So these are the these are thin shell black holes. The thin shell black hole is like is a single boundary solution. So what I'm drawing here is a Euclidean spacetime. The Euclidean time circle goes around, and to construct the thin shell black hole, we take a piece of the Euclidean of the ordinary eternal black hole, chop it off at some surface, which is the red curve here. That's where we insert the matter shell, and glue that curve to a patch of empty vacuum global AdS. Okay, so the solution in the end is the geometry is a portion of the eternal black hole outside the matter shell, glued to a portion of vacuum AdS inside the matter shell, and they're glued with the Israel junction conditions, which give equations of motion for the matter shell. By solving those junction equations, we get a trajectory for the matter shell, and then this gives us a solution for the thin shell black hole. Now, although we use the eternal black hole to construct this solution, it's a pure state. This is a single. It has just one asymptotic region, unlike the eternal black hole. There's one asymptotic region, and you should think of this place here where the shell hits the boundary as being an operator insertion in the dual CFT. So the partition function on this geometry is calculating a 2-point function in the dual CFT. The first insertion of V is here, and the second insertion of V is up here where the shell hits the boundary again. So V acting on vacuum creates a pure state, and this black hole is computing its norm. It's not a local operator, it's a spherically symmetric operator. Okay, that's the black hole, but now we can make wormholes by cutting and gluing K copies of the black hole. So we start with the wormhole. We start with the eternal black hole, the thin shell black hole. I'm not going to continue drawing the vacuum portion, but again, this red line here is the matter shell, which is glued to vacuum AdS on the inside. So we start with this thin shell black hole, and we chop it into pieces by cutting the geometry here, and then glue together several copies of that chopped up wormhole. So what I've shown here is what you get by setting K to 3. So if you choose this angle appropriately before you chop it up, then you can smoothly glue together 3 copies of this solution. And once we've glued together these 3 chopped up pieces of the thin shell black hole, this is now a 3-boundary solution. There's one boundary here, one boundary is this black line, and the third boundary is this black line. And each of these red lines is glued to a vacuum region, but they're all disconnected. So now we have 3 disconnected boundaries. A couple things to note about this construction. So that's the simplest version of this multi-boundary solution. A few things to note about it. First of all, that starting from any given thin shell black hole, there's going to be a maximum number of boundaries that we can get by this method. Because if I make K here too large and I try to construct something with too many boundaries, then this angle here needs to be 2 pi over K. But if I make K too large, then this will break down. These wedges that I'm drawing will intersect with the shell, and you'll no longer get a nice multi-boundary solution. So for any given black hole, there's a K max. Another comment is that we'd like to choose boundary conditions that correspond to K copies of our original CFT observable. So the original observable was a 2-point function, V dagger V, And we now want to have to k that to the kth power. So when we construct these multi-copy black holes, we fix tau 0, which is the amount of Euclidean time between the insertion of the matter shell and the time reflection symmetry point, which is where we're doing the gluing. So this gives you some boundary condition, which results in a k-dependent temperature for the black hole. That is, you have to, if you want to construct the wormhole for a given temperature black hole, you actually start from a black hole with a different temperature in order to fix tau 0 correctly.
Sorry, Tom, may I ask a quick question?
Sure. Yeah.
Maybe I missed it, but what parameters in the theory set the value of K max?
So that what's setting the value of K max is it's the type of matter. So this shell has a parameter, which is like the mass density of the shell, the energy density of the shell. So that's one thing. And the other thing is the original insertion point. So when we started with this black hole, there was a parameter tau 0, which was the original insertion point. So those two parameters, the tau 0 of the original black hole and the mass of the shell, determine for you the K max.
Okay, thank you.
So it's not so much fixed by the theory as by the matter content making up the black hole, exactly how you've constructed the original black hole. Okay. The other example that I'll tell you about are end-of-the-world brane wormholes. The construction here, and the reason I can do both of them is they're very similar to each other. So this construction is almost the same, except, so again, we start with the eternal black hole. But now on this red line, instead of thinking of this red line as a thin shell of matter, which is glued to empty AdS, this red line is now an end of the world brane where the spacetime terminates. And there's a tension parameter that tells you the energy density on this brane. So there's an equation of motion that you get for the brane. And again, we just have to solve that equation of motion for the brane to figure out the trajectory of this red line. So it's very similar to the case of the thin shell wormhole, but the equation of motion for the red line is a bit different depending on whether it's a thin shell or an end-of-the-world brane. There's an important difference when you work out the details, which is that the end-of-the-world brane black hole covers at most half of the boundary thermal circle. So it looks like what I've drawn here, where the brane always hits the boundary on the right half of this diagram. And since the brane hits the boundary on the right half of this diagram, that means that when you try to do this wormhole construction, where you chop this up into pieces and you cut out a wedge, that actually K max, the maximum number of boundaries you can make this way, is actually less than 2. Now that sounds a little strange because we're talking about K boundaries and K is not an integer, but actually this is consistent because these wormholes are K-fold symmetric. And what we can do is we can talk about the quotient of the wormhole by ZK. And once you take that quotient, the quotient geometry makes sense for non-integer K. So there's no problem with talking about these bulk solutions for non-integer K. And we'll find similarly on the CFT side that there's no problem talking about the CFT for non-integer K. And the two sides will agree even when K is fractional. So there are these fractional wormholes with K between 1 and 2 boundaries that have a consistent CFT interpretation.
Tom?
Yes.
So in this picture, where is the horizon?
So this is the Euclidean solution, and the horizon is the dot in the middle.
Okay, so What happens if you replace the black hole to just pure AdS? Anything goes wrong?
Let's see. Well, I don't think there's a solution like that, because so the way I described this, we started with the black hole and then we put in the brane, but that's just a trick for constructing it. Physically, the way you should think of this is that the brane carries energy, and the brane is back reacting to produce a black hole in the bulk. So once you insert a brane, you'll only find a nice solution like this if you insert the brane in the black hole background, and then that accounts for the back reaction of the brane on the geometry.
I see.
I also have questions. So here, when you decrease the tau zero a lot, so at some point it might be this horizon is excluded. So in that case, something special happen, or is it something transition, or nothing to do with the transition? So this red line just exclude this horizon if tau zero is very small. I mean, for example, extreme, I think it is extremely small. So
yeah, so the red line never comes outside. It turns out that the brane never comes outside the horizon, I believe.
oh, I see.
There is a there is an upper bound on the tension. If you so the tau zero is a function only of the tension and the black hole temperature.
Okay.
There's an upper bound on the tension. If you make the tension too large, then this brane will try to come back and intersect with itself. It'll come all the way around back this way. And we exclude solutions like that just by putting an upper bound on the tension.
Okay. Okay, thank you.
Okay. Yeah, so the positive tension ones always will sit behind the horizon. Okay, now we're going to turn to the CFT dual. There are at least two different ways to think about the CFT dual. One is by an ensemble average, similar to what's been discussed in JT gravity in the West Coast model. There, roughly speaking, well, this is, according to the boundary conditions, this is a contribution to the 2-point function v dagger v to the kth power. Now, in quantum mechanics, that of course can have no connected contributions. It's just a number to the kth power. But according to the JT random matrix duality, we might suggest that these wormholes calculate an ensemble averaged contribution to this 2-point function to the kth power. Now, in more than a 3-dimensional bulk, we don't have a detailed understanding of what this averaging would mean. We don't have a detailed understanding of what kind of average over what it means to do an average over CFTs, or what kind of how you would really define this quantity with a bar over it. So that's why I put the question mark here. You could posit that it's calculating an ensemble average, but we don't really understand what that means from a microscopic point of view. I'll have a few more words to say about that later, but I'm going to focus on the second possible interpretation, which is that we can think of these wormholes as replica wormholes for coarse-grained entropy. And this is an interpretation in a fixed CFT, where we're now coarse-graining instead of ensemble averaging. So that's what I'm going to turn to now. Coarse-graining using wormholes. Okay, let's step back for a minute, and I want to pose a question which a priori does not seem to be related to what I've been talking about so far, but it's a puzzle. Let's consider a pure state black hole with matter behind the horizon at t equals 0. In Euclidean signature, this is like, for example, the thin shell wormhole that we've been discussing, where you have some matter behind the horizon. The t equals 0 slice is shown here as the dashed line. In Lorentzian signature, The Penrose diagram for a black hole like this is here on the left. So the matter is behind the horizon. That's the thin shell. And the horizon exists already at time 0. Now, what you're seeing, these yellow lines here are the apparent horizons. Well, one is for vanishing outward expansion, and the other is for vanishing inward pointing expansion. And the event horizon is shown in gray. On the t=0 slice, the spatial geometry of this black hole looks like this picture. Okay, so if you have matter behind the horizon, then the apparent horizon is a minimal surface on that spatial slice, and the matter sits in a bulge behind the apparent horizon. Okay, so these black holes that we're talking about on the time 0 slice, it has an apparent horizon, which is, you can also think of as a subdominant extremal surface. It's subdominant in the sense of the Ryu-Takanagi formula. The Ryu-Takanagi formula tells you that the von Neumann entropy, the exact von Neumann entropy of this quantum state, is the extremal surface of minimal area. In this case, this is a pure state. The von Neumann entropy is exactly 0. It vanishes. And that matches the Ryu-Takanagi formula because there's a second extremal surface on this spatial geometry, which is the trivial surface, the nothing surface. Okay, because I can take this curve gamma, I can deform it all the way to the tip here and just shrink it off the tip, and I get a trivial surface, which is homologous. So the Ryu-Takanagi formula tells us that the von Neumann entropy of this black hole pure state is 0, and indeed it is. But there's a puzzle here, which is that well, we seem to have a horizon. That horizon is related to an extremal surface, but what is the CFT interpretation of this horizon? When we have a horizon, we expect its area over 4 to be calculating some kind of entropy, but it can't be calculating the von Neumann entropy because the von Neumann entropy is 0. So what is it calculating? Well, a natural possibility that has been studied earlier by Engelhardt and Wall is that the apparent horizon corresponds to some kind of coarse-grained entropy. I'll give a specific proposal for what kind of coarse-grained entropy. Engelhardt and Wall have approached this problem from a different angle, but basically a von Neumann entropy is the entropy if you know the density matrix exactly, and it vanishes for a pure state. A coarse-grained entropy is an entropy that can be non-zero in a pure state, because it's defined by forgetting some information about the pure state and then calculating the von Neumann entropy. What I'm now going to do is explain how we can use wormholes to understand exactly what coarse-grained entropy is corresponds to the area of an apparent horizon like this one. The strategy to understand this coarse graining is the following. Given a pure state black hole rho, we will first find the replica wormholes, that is the bulk solutions, that branch around the apparent horizon. That is, we'll replicate the manifold by gluing together multiple sheets that go around the apparent horizon, and then allowing that multi black hole spacetime to back react so that it solves the equations of motion. Now, if we can find those wormholes, which in some cases we can, the next step is to find a density matrix rho bar in the dual CFT, whose replica partition function trace of rho bar to the k matches the gravitational action of the wormhole, or the gravitational path integral for that wormhole. If we can find a rho bar that satisfies this equation, then we'll interpret that rho bar as providing us with a coarse grain density matrix. So we started with a pure state rho. We construct the wormholes, and then we look for a new state, coarse grain state, rho bar, that reproduces the wormholes. Now, if you can find such a state, then by construction, the von Neumann entropy of rho bar is equal to 1/4 the area of the apparent horizon in the original black hole. Because by taking k near 1, we can, on the right-hand side of this equation, by taking k near 1, we can get the von Neumann entropy, minus trace of rho bar log rho bar. And similarly, on the left-hand side of this equation, by taking k near 1, we can use the gravitational replica method of Lefkowitz and Maldacena to show that the left-hand side of this gives the area of the apparent horizon. Okay, so that's the strategy. And it's ambiguous up to unitary transformations. The way I've described it, it's ambiguous under unitary transformations of rho bar. But the goal in life of this rho bar that we're constructing is to give us a microscopic CFT formula for the area of the apparent horizon. So that's our goal here. It's to find a CFT formula for the area of the apparent horizon in a pure state. For those purposes, this unitary doesn't matter. We just want to be able to calculate the entropy microscopically. I sort of think of this as a derivation of the Ryu-Takanagi formula, but done in reverse. Okay, in the Ryu-Takanagi formula, you want to calculate the von Neumann entropy. You have some state rho, and you want to calculate the von Neumann entropy. And Lefkowitz and Maldacena showed us how to do that using the AdS CFT dictionary. You find the replica solutions that calculate trace of rho to the k, and then you take k near 1, and you conclude that the von Neumann entropy is area over 4, the Ryu-Takanagi formula. Here we're doing something a bit different. We have a subdominant surface, and we want to understand what density matrix it's the von Neumann entropy of. So we sort of follow this in reverse. We construct the same set of wormholes, but now branched around the subdominant surface, and use those wormholes to figure out what rho bar is.
Hello.
Yes.
So you mentioned the pure state black hole. And is there any geometric notion then what is the mixed state black hole?
Well, the eternal black hole that we often talk about is a mixed state black hole, in the sense that if you look at only a single, so the eternal black hole has two boundaries. In the Lorentzian picture, there's two boundaries. It's not a wormhole in the sense of the wormholes we're talking about, because that's two Euclidean boundaries. But the eternal black hole has two Lorentzian boundaries. And if you just look at one of them, the CFT is in a mixed state. It's in the thermal state. So that is called a mixed state black hole, as opposed to the pure state black holes, which are supported by some matter behind the horizon.
So whenever you have a more than two Euclidean boundary, maybe, then that's your definition of mixed state black hole?
No, let's see. I would call a mixed state. I would call a mixed state black hole if you in cases where if you take the density matrix associated to a single asymptotic region of the Lorentzian spacetime, if that density matrix is mixed, then it's a mixed state black hole. If that density matrix is pure, then it's a pure state black hole. But this is really a simple, it's an easier distinction than the way I'm describing it. It's really just a question of whether the state you're in, so you're in the fundamental theory of quantum gravity, the full theory, you're in some state, and
Right.
that's either a pure state or a mixed state. If you started out like with a star that was in a pure state and the black hole formed by collapse, it's still in a pure state. So those are the pure state black holes. Whereas if you form some entangled state like the thermal field double, then you're talking about a mixed state black hole.
So I guess that the question is, in order to have some mixed state, we need some algebraic sum of the rows. And how such algebraic sum of a row can be represented in geometric context.
Well, geometrically, the mixed states are represented by having an Einstein-Rosen bridge. So let me go back to the picture here. Here in the Lorentzian picture, if we look at time zero, the time zero spatial slice has only one asymptotic region. That's the picture that's drawn over here. The fact that there's only one asymptotic region means there's nothing to be entangled with. And so here we're talking about a pure state black hole. If I had drawn the ordinary, if I had drawn here the eternal black hole Schwarzschild-Penrose diagram, instead of having the matter shell inside the black hole, we would have a second asymptotic boundary. And these two boundaries would be entangled. So the fact that it's mixed is being represented by that Einstein-Rosen bridge. And if we were to focus on just one of those boundaries, we would be in a mixed state.
All right, thank you.
Okay, so I'm going to go through how this works for the example of the thin shells and the B states. And tell you the density matrix that results from this procedure. So our goal here is to find an explicit formula for the coarse grained density matrix, and I'll say how this works out in this example. So let's start by just expanding the original black hole and energy eigenstates. This defines some expansion coefficients, AN. Now, the density matrix of the pure state of this black hole, we get just by taking the bra and the ket. And that is this double sum over energy eigenstates with AM, AN star. So that's our starting point. It's a pure state density matrix. And now we want to apply this coarse graining procedure. In step one, we find the replica wormholes. In this case, we're looking for wormholes that duplicate by gluing across the apparent horizon. And those are exactly the kinds of solutions that I discussed in the first part of the talk. So the replica wormholes for this are simply the Euclidean solutions, K-boundary Euclidean solutions that we discussed earlier. You construct them by cutting and gluing multiple copies of this black hole at a different value of the temperature. Once we have those wormholes, we need to then find a density matrix that reproduces their gravitational action. I'm going to skip the details of that calculation, but you can calculate their action and just compare to the density matrix in the dual CFT in order to determine rho bar. And the answer that you get is the following. In these examples, the coarse grained density matrix is the diagonal projection of the full density matrix. So rho bar is just the diagonal part of the density matrix rho. You can find that diagonal part explicitly and find its weighting factor. I've written here the answer that we found in the limit of the planar black hole which is a high temperature limit, but you can find the general solution. It just is a bit more messy to write down. You can't find it exactly because the exact density matrix is going to be sensitive to the UV physics. It's going to depend on the details of the UV completion, and we're working here with a low energy effective theory. So we can't find it exactly. There are these order 1 coefficients here that are undetermined and UV sensitive, but up to those order 1 coefficients, you can find this. You can find a coarse grained density matrix rho bar. So the defining feature of this coarse grained rho bar density matrix is that its replica partition function, trace rho bar to the k, reproduces the wormhole action. So that is, we designed this rho bar in order to reproduce the bulk wormhole action. Note that in this expression, trace rho bar to the k, that k can be non-integer, and that matches the fact that the wormhole can exist for non-integer boundaries. And this match between wormhole action and CFT replica partition function is for any value of k up to k max. They also agree about the value of k max, where the saddle point stops existing. The conclusion then is that the microscopic CFT formula for the apparent horizon area is the von Neumann entropy of the coarse grained density matrix. So the area of this apparent horizon is the von Neumann entropy of rho bar, the diagonal projection. Now, in fact, this von Neumann entropy of the diagonal projection is something that has been discussed before. This is a quantity that's been discussed in the condensed matter literature and is called the diagonal entropy. It's introduced by Barankoff and Polkovnikov in the study of quantum mechanical systems out of equilibrium. They were looking for a notion of entropy that could be applied to pure states in quantum systems, in chaotic quantum systems, in order to study their non-equilibrium evolution. And they came up with this one long ago and showed that it obeys some nice properties. In particular, it obeys a thermodynamic-like first law, assuming that the quantum mechanical system obeys eigenstate thermalization. And it obeys a second law of thermodynamics under stochastic evolution. So by going through this procedure, somewhat to our surprise, the answer that we land on is a very nice one and a very natural one. It's this diagonal entropy that was proposed as a coarse-grained entropy in condensed matter. This is the answer we get by our procedure in the case of thin shell black holes and these end of the world brane black holes when there's no additional matter. So this actually will not be the answer in general, as I'll explain in a minute. So to get something a little bit more elaborate, let's consider what happens when we add a massive particle outside or inside the black hole. So we're going to take the same black holes that we've been discussing and just add one extra particle and ask how that affects this procedure. And we have two choices. We can add the particle behind the horizon. So here, the red line is the thin shell. That's the thin shell that makes the black hole. And the blue line is a probe particle on a space like geodesic. We can add that particle behind the horizon, or we can add that particle outside the horizon, just by putting the geodesic to the right. And intuitively, when we go through this coarse graining procedure, we expect there to be a sharp distinction between whether the particle is behind the horizon or outside the horizon. If it's behind the horizon and we coarse grain, then the particle should get coarse grained away. If the particle is outside the horizon, then the particle should survive the coarse graining procedure. This is not getting hidden by the horizon. So we expect a sharp distinction in these two cases. And that's in fact exactly what happens. Because when you now construct the wormholes for this black hole plus particle, two different things can happen. The particle you can have wormholes where the particle the dominant solution is one where the particle travels through the wormhole. That's the case here that I've drawn. Or you can have solutions, wormhole solutions, where the particle stays outside the wormhole, like in this case on the right. And when you go through this coarse graining procedure, the answer that you get depends in a discontinuous way on whether the particle goes through the wormhole or stays outside. If it goes through the wormhole, you get again the diagonal projection that we had before, and that particle gets coarse grained away. If the particle stays outside the wormhole, then you get something a little bit different. The coarse graining map that defines rho bar is no longer the diagonal projection. Instead, it's a more complicated procedure where you project onto the diagonal inside the action of these operators. So put into words, the map is to strip off these extra operators, project onto the diagonal, and then put those operators back. So you get two different answers, and the answers that differ sharply depending on whether the particle is inside or outside the black hole. And it matches our intuitive idea about what should happen when you coarse grain. Okay, I'm going to conclude with just a few comments and extensions, related work. So one comment is that is on 3D gravity. So in 3D gravity, you can do quite a bit more than what I've described here. In 3D gravity, so what I've described in general dimensions are spherically symmetric wormholes. And so they're quite special in that respect. In 3D gravity, all solutions of the Einstein equations are locally AdS3. And so it's much easier to construct solutions without having spherical symmetry. So we've constructed a number of multi-boundary solutions, including all the ones pictured here. You can have two boundary solutions with matter sources that are not spherically symmetric. Like in this case, these are point-like matter sources. You can have wormholes that have higher genus topology through the wormhole. You can have many boundary versions of this. So this over here is a 3-boundary wormhole with some number of particles going through point-like sources, going through the wormhole and connecting the various boundaries, and so on. There are many, many solutions that you can construct in 3D gravity in great detail. You can also go further in the CFT interpretation in two-dimensional CFT using the power of the Virasoro algebra. And in this case, we can see that there are two different but compatible interpretations for these wormholes. The first one is just what I've described in this talk, that you can construct replicas for a coarse-grained density matrix using these types of wormholes. So that in that case, it's quite similar to what I've been describing. But in 2D CFT, we also understand what it means to do an ensemble average. Because in two-dimensional CFT, we can understand 3D gravity as arising from a large central charge approximation to a two-dimensional CFT. And we can then do an ensemble average over approximate solutions to the bootstrap equations of the two-dimensional CFT. So that gives you another way of thinking about this that's similar in some ways to the ensemble averages discussed in JT gravity or the West Coast model. I'm going to skip this comment and jump to my last slide, which is about applications of this to more real-world gravitational instantons. So I focused on the construction in AdS because there we have AdS CFT to guide us. And we can talk about the microscopic interpretation in dual CFT. But actually, this procedure that I described to construct multi-boundary solutions, this cut and glue, where you take the eternal black hole, you chop it into pieces and you glue them into multi-boundary wormholes, can be applied to any locally eternal black hole. For example, you can apply this to the Oppenheimer-Snyder to the famous Oppenheimer-Snyder solution, which describes a collapsing star in asymptotically flat space with an FRW interior and a short shield exterior. Now, in principle, this gives you gravitational instantons, which contribute to physical processes in the real world and in asymptotically flat, in an asymptotically flat background. And basically, it's hard to do these calculations, but in principle, it gives us a contribution to the many point function of something like a particle in the standard model. You can use it in principle to calculate scattering amplitudes, and it would be the leading effect to certain symmetry violating processes. For example, if you take an operator that violates B minus L conservation and raise it to the 10 to the 19 power in order to be able to support a wormhole, then it should be possible to construct gravitational instantons that contribute to this amplitude and give you a direct way of calculating these symmetry violating effects that have long been understood to exist in quantum gravity from general arguments. And I'll conclude here, and thank you for your attention.
Thank you, Tom, for the very interesting talk. Are there any questions?
Yeah, I have some very basic questions about the gluing to space-time. So should we consider this gluing surface as a kind of a horizon?
No, the gluing procedure is really just a trick. It's a smooth. All right, let me go back to the picture. Let's see, the horizon. So in this picture, the horizon is the point at the middle, because this is Euclidean. The Euclidean time goes around on this picture. And so the Euclidean horizon is the place where the time circle, the Euclidean time circle shrinks to 0. That's the point in the middle. This gluing surface is not like the horizon. It's like a t=0 slice. It's like the it's the point where the Euclidean section turns into the Lorentzian section.
So the question is, can you include the this eternal black hole as your particular example, or that is a very exceptional case to your procedure?
Are you asking whether it's possible to construct more general wormholes by gluing when you do not have the eternal black hole?
No, I mean whether we can, visualize or construct the just eternal black hole in your
the ordinary eternal black hole.
Right.
No, that's not a special case of this. The ordinary eternal black hole has only one Euclidean boundary. And it's a full thermal circle. So the distinguishing feature of the eternal black hole is that the thermal circle is a closed circle. So the black line would go all the way around and close on itself. And here it's important that the thermal circle is cut off by the matter. And that's what makes it a pure state black hole instead of an eternal black hole.
Thank you for clarification. Okay.
Are there any more questions, maybe from online? I have a couple of maybe a bit naive questions. So the first one, in your construction of the when you consider the apparent horizon, so what guarantees that the apparent horizon is an extremal surface on one hand? And my second question is whether you can extend somehow these wormhole constructions to non-extremal surfaces.
Good. Okay, so apparent horizons in general are not extremal surfaces. So if we look at this diagram, everywhere on this curve is an apparent horizon where the outgoing expansion vanishes, but only this dot here is also extremal because both expansions vanish. If you have a time symmetric apparent horizon, then it's also extremal.
Nice.
Because apparent horizon means theta plus is 0, but if it's time symmetric, then theta minus is also 0. So time symmetric apparent horizons are always extremal. Now, for the second part of your question, could you apply it to an apparent horizon that's not extremal? Say we want to cut it up here on the yellow line somewhere.
Right.
In detail, so we don't know how to do that. It's a good question. There's work of Aaron Wall and collaborators and Netta Engelhardt and collaborators who have shown how to take a apparent horizon, the region outside any cross section of the apparent horizon here, and to change the space-time in a way that that you find a extremal surface of the same area. Okay, so they basically chop off a piece of the space of the Lorentzian space-time, and they construct a new space-time and glue it in. So they sort of, roughly speaking, have a way of turning apparent horizons into extremal surfaces. That's a bit quick. It's not quite what they do, but I mention it because perhaps a procedure like that could be used for our approach as well.
I see. Thank you. Are there any more questions? Then maybe I can ask one final one, which is related to this diagonal entropy that you were discussing. So how do I reconcile this idea of disorder from the quantum information perspective that this diagonal entropy is measuring with the idea of this the area of the apparent horizon or some coarse graining procedure? How do I reconcile these two ideas?
Well, in this case, it's not disorder in the sense of disorder like in SYK.
So sorry, non-equilibrium. Sorry, non-equilibrium.
Non-equilibrium. Well, this is a non-equilibrium situation because there's this matter shell that's falling into the black hole. So this also is a far from equilibrium situation in gravity. So I think it's quite similar. It's quite similar. You have a pure state with 0 von Neumann entropy, which is far from equilibrium, but behaves as if it had entropy given by the area of gamma over 4. And just as the condensed matter theorists wanted to quantify that entropy and came up with the diagonal entropy, the wormhole procedure led us to the same conclusion.
I see. So in the case, for example, that you were mentioning, these extensions by Wall and collaborators to these proxy surfaces which have the same area as the apparent horizon, but which are extremal. I mean, you can also compute the diagonal entropy in these cases, or maybe, I mean, you have the same interpretation of the entropy in this case, maybe.
Well, let's see. It would be necessary. I don't really know the answer, but I think something more elaborate is needed because even just to specify a point on this curve, like say this point here, you need to somehow cut off the diagram to only include the stuff outside that point. So for example, anything in the past way back here should be excluded somehow.
Mhm.
And the diagonal projection doesn't do that. Okay, so I don't know how to do it, but something more elaborate is going to be needed to be able to restrict to a certain causal diamond.
I see. Thank you. If there are no more questions, then let's thank Tom again for the very nice talk.